Greetings, Algebra 2 students. I appreciate you finding time to tune in and get your notes taken care of. We are looking at a unit test, Unit 7, on Thursday. So this is probably going to be the last of the new information that we're going to be looking at going towards the new test. Then on Wednesday we will have some different representations, so it'll be some of the same information, review type information, but possibly some different presentations of it, so maybe some word problems and working with some different formulas and stuff like that. Okay, so this will probably be the last of the new information, if you really even want to call this new information, because it's basically the same stuff we did last unit, just with a different function. So today we're looking at the inequalities with the rational functions. Our objective for the day, the student will learn to determine how an inequality affects the solution set for a rational function. Now, looking at my objective there, I see I have used the wrong homonym effects, should be with an E. E-F-F-E-C-T-S. I apologize for those of you literary people that are probably criticizing me for getting that wrong. At any rate, copy down your title, Inequalities in the Rational Function, and your objective. Press pause anytime you need more time to copy something down, and then hit play when you're ready to move forward. Okay. Now, this is should have the same type of feel as it did when we went through the square root functions, because really not much is going to change at all. From years of studies of graphs, we should know by now that an inequality, or in an inequality, any point that exists on a curve in a graph is potentially a solution to the equation for that curve. However, when equalities change to inequalities, the set of all points that exist in the space that's on one side or the other of that curve are in the solution set as well. As a matter of fact, many business type applications in the real world operate not in equalities but in inequalities when they're trying to figure out how their parameters for doing business, their profits and losses and margins and things like that, deal in inequalities of multiple different situations as opposed to equalities. In the real world, it's actually pretty difficult to get exactly onto a particular curve. Okay, but we become very interested in what's going on in one side or the other from that curve. Okay, so let's take a look at a couple of things. Okay, just speaking generally here, okay, not necessarily working this equation, okay, but just reinforcing what we said just a moment ago. For any equation that we have in mathematics, any point that exists on this curve or line or whatever it is, okay, any point x comma y that is on the curve is a solution to the equation of that curve. And I gave you a graph, okay, of what this particular curve looks like. Obviously, it's a rational function, so it generates a hyperbola. And here are some potential solutions that would go along with this equation and this hyperbola. But of course, there are many more points than just these four that I have marked and listed. There are infinite points, infinite coordinates, infinite ordered pairs that show up on this graph. So there's infinite solutions to the equation. Okay. Now, as we already know, okay, and we're seeing again today, when inequalities become the deal as opposed to equations, okay, then there are even more solutions. Kind of hard to think about that when you think there's already infinite solutions, and now we are going to find more than infinite. Well, true enough, infinite means it is uncountable, that there are so many, and now there come more, but it is still infinite, uncountable. Okay, we find even more solutions. The thing that is going to be different this go round in this unit than we saw in the last unit is going to be the way that the shading appears in the graph. Now, let's say that we take this same equation from the top of the screen, and instead of an equation, we allow it to be an inequality of some kind. Now, when we did the square root function, we saw very easily that we had to shade a particular direction from the graph. Now, that's nothing new. That's just the way inequalities work. The difference was with the square root function, there was only one thing in the graph, so you shaded one way from that one thing, either up or down or left or right from that one curve. But of course, with a hyperbola, you have two curves running around in the graph as the result of the one inequality that we have. Okay, so we will be shading one direction, either up or down or left or right, but since there are two curves in the graph, the result will be that more of your graph will end up shaded than we saw with the square root functions. Okay, so in this particular case, the equation said that y would be smaller than or equal to that expression. So of course, y being smaller than or equal to meant that it was shaded downwards because that's where the values of y are smaller. Okay, so let's step forward, or actually step backwards, whichever way you want to look at it, and reinforce some of the same stuff that we said when we went through the square root unit. Okay, the same ways to manage inequalities still apply. So this is review, but write it down again anyway because it still applies. Okay, if your variable is already isolated, okay, that is obviously very easy to do the shading. If the variable is already isolated, we simply shade in the direction of that axis according to which way the inequality is positioned. So if the problem wants to say y is smaller, then we shade downward. If the problem wants to say y is larger, then we shade upwards. Now, we haven't really looked at many inverses this go round, but they are still out there. So if the problem wants to say x is smaller, then we'll shade to the left because that's where the small values of x are. Or if it wants to say x is larger, then we'll shade to the right because that's where the larger values of x are. Okay, so the same stuff still applies. Let's take a look at a couple here real quick. Okay, press pause if you need a minute to scribble this down. And we have a couple of inequalities and the graphs that accompany them. Okay, and all we're doing is just getting the shading part done. The equation on the left, or the inequality on the left, says y is greater than or equal to the expression negative of 2 over x plus 2 plus 1. Okay, so y is greater than the curve. So we just ask ourselves, okay, where are the larger values of y? Obviously, the larger values of y are upward. Okay, so I'm just going to take this one curve at a time. I'm looking at the one in the second quadrant for starters. And in order for y to be larger than the curve, then that would mean the area above the curve is shaded. Okay, so there is that half of the shading. And then from the curve that is down in the fourth quadrant from the center, okay, again, it's still y is larger. So where are the values larger than this curve? Well, they are still upwards. Okay, so we're going to shade from the curve upwards. Okay, so there is adequate shading for the inequality where y is larger than this curve. Over on the right-hand side, here we see an inverse. We know it's an inverse because of the way the variables are positioned in the inequality. X is smaller than or equal to the reciprocal of 3 times y minus 2. Okay. So again, let's look at it and go, okay, where is x smaller than this curve? Okay, well, I'm looking at the first curve I'm looking at is the one that is in quadrant 3 from its center. Okay, and the smaller values of x are off to the left. So I'm going to shade leftward from the equation. And then on the second part of the hyperbola, again, this is the one in the first quadrant. Where are the values smaller than x? Well, once again, the values of x are smaller going to the left. Okay, so it's the same idea, just multiple curves to consider rather than just the typical one curve that we've been used to over the years. Okay, so moving forward, that's an easy way. If the variable's already isolated, you can just shade in the direction of that axis according to which way the inequality is positioned. Now, another thing we said as far as our shading is, well, what happens if our variable is not isolated? Well, if the variable is easy to isolate, then that is certainly a justifiable way of going about it as well. If you can get the variable isolated, then you can do exactly as we did from above. And lastly, okay, if all else kind of fails, your last resort catch-all method would be to pick a test point in open space. Okay, pick a test point in open space, plug it into your inequality, and see if your inequality likes it or not. The inequality will either give you a true statement or a false statement, okay, if we select good points, and here is what we would be expecting. Okay, if we pick a point and we plug it into our inequality and our inequality likes it, it's going to give you a true statement. If it is a true statement, then that means that the inequality likes that point and it should shade towards that point. If you pick a point and you plug it into the inequality and the inequality does not like it, in other words, it gives you a false statement, then the inequality is saying, no, I do not like that point, do not shade toward it. Now, when we did the square root functions, we also had the possibility of picking a point and plugging it in and ending up with an imaginary result. Well, we do not have the possibility of getting imaginary results this go round because we do not have any radicals in our rational functions. Okay, but it is possible that you might pick a point and plug it in and end up with an undefined statement. In other words, your denominator of your fraction might try to equal 0. So if you end up with an undefined statement as a result of a point that you have picked in open space and plugged in, what you have done is you have picked a point that is on one of the asymptotes. You need to get off of that asymptote and pick a point, a different point out in open space and try again. Okay, let's take a look at a couple of examples from scratch, see if we can figure them out, and that'll be it. Okay, graph the solutions for y is less than or equal to the reciprocal of x plus 2 plus 3. Okay, off the bat, we should know a little bit about this graph and the information going along with this graph. But in all reality, we're probably going to have to do a little bit of plotting method to figure out exactly what the graph is doing. So we ought to be able to pinpoint the center of the graph, and we also ought to be able to pinpoint the direction of the graph. Now, we could be able to tell information about the speed as well. Okay, but that's not critical in order to get the equation or the inequality into the graph. Now the center point is located where? Okay, it looks like we have an h value of positive 2 right there in the denominator attached to our x value. And we have a k value of positive 3. So it looks like a center point at negative 2, positive 3, reading out of the equation. So there's going to be our center point, and that's good information to know. That way, if we have to do the plotting method and start picking some values, we know where to pick them from. Okay. Now direction is a good thing to know as well, because now we have a center point. We basically have a real good idea of what's going on as far as our asymptotes, and there should be no reason for us to cross the asymptotes. So that kind of gives us, it narrows down where our points are going to end up in our graph when we start plugging values in and getting coordinates back out of it. Okay, looking at the inequality, I do not see any sign change associated with the rational part of the equation. It is positive, okay, which means our direction is normal. Okay, and that will mean that the graph will exist in quadrants 1 and 3 from its center point. So we absolutely should not have any values in the second or the fourth quadrants from our center point. Okay. Now the speed is normal, which means that our graph is going to be moving away from its center point at the standard or parent speed. Okay, but however, I'm going to pick some points here. I'm going to plug into the equation or into the inequality and find out where the graph is going. Okay, I'm going to come start from the center point. I'm going to come to the left first and go from there. Now we already know that we have the center lives at +2, and it will be, of course, undefined from there. So I'm going to come backwards a little bit. I'm going to move backwards from 2 to 1, 1 to 0, 0 to -1, see what kind of values that gives me, and see if that gives me enough information to graph this thing or not. Let's see, when x is 1, we're going to plug into the denominator right there, and that would put a 3 in the denominator, okay, a 1 in the numerator, so that fraction is 1/3. And when you add that to the whole number 3, you get 3 and 1/3. Okay. Plugging 0 in, of course, that makes the denominator 2, so that fraction is 1/2, plus 3 is 3.5. When the x value is -1, that would make the denominator +1. 1 over 1 is 1, plus 3 is 4. I'm going to transfer these coordinates into the graph and see if that's enough information to get the graph going here or not. Uh-oh, I have made a major mistake, and my mistake was I did not get the negatives correct. Okay, should have been a -2 on my x-axis. Okay, so let's see what that actually does. I still would need a -1 and a +1. So as it turns out, I accidentally messed this up in a way that can still work. Now let's see what we have here. I'm going to have a coordinate at 1, 3 1/3. No, I'm not. I don't know what I'm talking about here. Just ignore me at the moment. I need some better values here. From -2, I should have gone to -3, -4, and -5. Many apologies on that. Simple sign errors can cause us all kinds of trouble. Anyway, when x is 2, plug it in. That would be a -1 in the denominator, so the fraction would be -1, plus 3 would be +2. -4 in the denominator would be -2 overall, be -1/2, plus 3 is 2.5. -5 for x would give a -3 in the denominator, so that's -1/3 overall, plus 3 is 2 2/3. Okay, let's see if that translates a little better to the graph. -3, +2 would be a point right about there. -4, 2.5 is a point right about there. And -5, 2 2/3 is a point right about there. Okay, using those 3 points plus the asymptotes, we're able to get this part of the hyperbola going pretty easily. Okay, so now I'm going to go to the other side of the center and pick some other points. Hopefully I won't mess this one up. From -2, I'm going to go to -1, 0, 1. Well, those points would have helped me just a minute ago. I just didn't see it coming. Let's see what we have. -1 would give us 4. 0 plugging in there would give 3.5. 1 plugging in there would give 3 1/3. So there's those values I needed just a moment ago. I just didn't recognize that they were going to apply over here. -1, 4, I just marked. 0, 3.5 is there, and 1, 3 1/3 is about there. And again, we get a pretty good idea between those points and the asymptotes that there is the hyperbola. Okay. I'm going to go ahead and get rid of my x's. That was actually the thing that tipped off to me that I was plotting information in the wrong place. Those x's, I kept trying to get points that were in the quadrants 2 and 4. Anyway, let's look at the direction here. I drew these lines as solid lines. Okay, but again, that's always something that I just kind of accidentally do. I always want to draw the lines solid, but the question is, should they have been solid or should they have been dashed? Well, let's look at the inequality. A solid line would be an equal inequality, and a dashed line would be a non-equal inequality. Okay, since it says y is less than or equal to, then the solid lines were actually the correct deal. So I got lucky on the drawing end there. And the inequality says y should be smaller than. or equal to? Well, from the two curves, where is y smaller? Of course, smaller means downward. Okay, so I'm going to shade downward from the graph there, and also downward from the other side of the hyperbola. So any value along either of these curves or in the green shaded area would satisfy this inequality. Okay, let's take a look at one more. Hopefully I won't mess this one up. This time we do not have a variable isolated. Okay, so we're going to have to either get the variable isolated or just simply take the inequality as it is written and perhaps pick a test point. Personally, I think I'm going to get the variable isolated. It is not a big challenge to get that y by itself. First thing I'm going to do is I'm going to move that -4 to the other side. That'll give me negative y is greater than 1 over x minus 3 plus 4. Okay, and the final thing would be that we do not want a negative y, we want a positive y, so I would basically take the entire equation and hit it with a negative sign. That's going to reverse the direction or the signs of all of the terms in the problem, but it also does something very important. Remember, if you multiply or divide an inequality by a negative sign, you change the direction of the inequality. So that's going to be important. If you miss that, it's going to make you shade the wrong direction. Okay, so there is our new equation with the variable now isolated. Okay, so let's get a center point for this graph. See if I can do this one without messing it up. It looks like our h value is at +3, right there in the denominator attached to x, and our y value is at -4. So +3, -4, looks like a center point right about there. Okay, and that will give us asymptotes running across like that. And like that, so our graph should not cross those boundaries. Okay, and the term that has x in it, it is a negative value instead of a positive value. That means the graph is going the incorrect direction. So this time we are not in quadrants 1 and 3. We will be in quadrants 2 and 4. Let's see what the points are going to look like. Okay. So from the x value of +3, okay, let's see if I can't get this right this time. This time I'm going to move 3 steps to the left, and then I'll come back and move 3 steps to the right. Let's see what happens. Okay, when x is 2, plugging into the denominator, 2 minus 3 would be -1. That gives us a fraction of -1, but there's also a negative outside of that fraction, so it's a +1 minus 4 should be -3. When x is 1, that would be 1 minus 3 in the denominator. That's -2. So that fraction is -1/2 plus a negative outside makes it a +1/2 minus 4 is -3.5. When x is 0, obviously the denominator is -3. So that fraction is -1/3 plus the negative outside is +1/3 minus 4 is -3 and 2/3. Let's take this information to the graph, see if it's looking good so far. Got a coordinate at 2, -3. That is about there. We've got a coordinate at 1, -3.5. This is about there. And 0, -3 and 2/3 there. Well, between those 3 points and the asymptotes, we got a pretty good boundary for our curve. Okay, now I'm going to take these points away and I'm going to do the same thing to the other side of the center. Okay, so from 3 I'm going to move up to 4, up to 5, up to 6. Should give us a pretty good idea. When x is 4, plug into the denominator. 4 minus 3 would be +1, so the fraction is 1 over 1. But the minus outside makes it a -1. So -1 minus 4 is -5. When x is 5, the denominator would say 5 minus 3. That is a 2. So we have a fraction of 1/2. The negative outside makes it negative 1/2 minus 4 is negative 4 1/2. When x is 6, that would give a denominator of 6 minus 3 is 3. 1 over 3 is the fraction. The negative outside makes it a negative 1/3 minus 4 is negative 4 1/3. Okay, we transfer these guys to the graph. 4, negative 5 is there. 5, negative 4 1/2 is about there. And 6, negative 4 1/3 is about there. And between the 3 points and the asymptotes, we end up with that graph. Okay, I'm going to get rid of my x's that I put in the quadrants. There we go. And then let's shade. I messed it up. I absolutely messed it up. Look what I did. Okay, the inequality does not have an equal sign. Okay, it does not have an equal sign, so I should not have drawn my lines solid. They should be dashed lines. Okay, so kind of difficult to do on the smartboard here without messing up the entire diagram. Okay, so I'm going to kind of fill them in with dashes rather than solid lines. On your paper, using your pencil, you would be able to erase yours and draw it correctly. Okay. And the equation says y is smaller than the graph. So once again, from the equations that we have, we're shading towards the smaller y values, so downward from each of the curves. So that is what it would look like. I apologize for the errors on my behalf. Okay, but that's why we write in pencil. We always make mistakes, so easy to be able to erase them. I appreciate you taking time to get your notes taken care of. I apologize for them being a little longer than normal. At any rate, this, like I said, this should end up being the last of the information going towards the next test. So again, I appreciate you taking time to get your notes done, and I'll see you in class.